We are a lab that's in central engineering, and we're pillared on 4 key foundational capabilities. The first being model-based software development, followed by low-cost test beds, risk reduction in the form of rapid prototyping, and finally early life cycle testing. These 4 capabilities translate into 3 different product domains for us. The first being our modeling domain, which includes flight software models, command and data handling models, and finally space vehicle components. Secondly would be our services-based products, which include website and SharePoint, lab management, marketing, etc. And then finally, our simulator domain. Now, as I mentioned previously, many of our simulators are introduced early on in the life cycle. One appealing aspect of this particular undertaking was that it allowed us to retrofit an existing simulator with a more modern technical solution, thereby allowing us to enter into an adjacent market and improve our simulator capabilities in the lab. So some background on the GPSIIR modernization effort. The customer basically approached us and said, we have a simulator, we want to use it for the next 20 years. Can you make it more modern? Can you give us better fidelity for our testing? So we began to research this. Basically, their simulator platform allows them to validate flight software prior to uploading to on-orbit assets. It consists of 2 main components, the SPU, or Spacecraft Processing Unit, and the STE, or Specialized Test Equipment. So this slide gives you kind of a visualization of the current system architecture. Now, as I mentioned, there's the SPU and STE, and you'll see a third box known as Gypsum, which is the repository for the models, and for this particular effort remained unchanged. So as we began our research, we needed to figure out a spot as to where to insert our technical solution. We thought about connecting directly to the SPU, however, that introduced the issue of connecting to high-value hardware, and so we shied away from that. And as you'll see, the STE is comprised of 2 other components, the STE hardware, which consists of the custom interface boards, which connect to the SPU, and then the STE Computer. We thought about replacing the STE altogether, but realized we could leverage the existing custom I/O boards and just focus on the STE Computer, and that's where we turned for this effort. So the current STE Computer is an HP 1000 A990 device. It consists mostly of circa 1990s hardware. So the customer also expressed an interest to have a configurable solution. We believe this is mostly because in order to test certain elements of flight software, it requires they disable certain pieces of the STE. Also, the STE Computer runs software that's written primarily in assembly, which is a difficult skill set to find and very difficult to configure and maintain. With that in mind, we began our trade study of different solutions. The first one we came upon is a Lockheed Martin solution known as the Hardware Interface Box, or HIB. We initially thought this would be a good fit. However, the custom nature of this device and also the fact that it lacked the number of I/O that we would need to meet the specifications create some issues. We also felt that since this is a custom device, it requires a unique set of skills in order to configure and maintain, we'd rather go another route and find a design that we can maintain on our own within our lab and therefore offer to other customers. So with that in mind, we transitioned to other commercially available products. We began looking at a VME COTS approach, and although this seemed appealing because it offered a low-cost solution, there were issues in terms of using multiple vendors and how that would affect configurability and maintenance, and also if that would bring obsolescence into the picture down the road. Also, we felt that using VME COTS wouldn't necessarily create a solution that we can market to other programs, and we were looking to maximize the reuse of this solution. With that in mind, we began looking at a potential NI PXI-based system. We turned to this mostly because we like the proven track record of NI in this domain. Also, they were able to offer us a solution that not only had the I/O, met the I/O restrictions we needed, but also the ease of their configurability of their system. We were able to acquire a chassis, get the controller, get the appropriate cards, put them together, and within an afternoon we were toggling I/O lines. So we felt this would allow us to meet the aggressive schedule we had, given we were trying to provide the customer with a proof of concept demo. Also, we like the idea that we'd be working in one environment, which is their software environment, LabVIEW, which would allow us to make use of their high-level software components for our design. One of the things about the HIB that kind of diverted us from that was that maintaining it, like I mentioned, you needed many different skill sets. We like the idea here that you could use their high-level software components to create DMA FIFOs, control I/O, use control methods, use different I/O methods. We like the idea that you could basically do that all in one environment, and it would abstract that away and allow us to get directly to meeting the specifications for the system rather than setting up its configuration. So this is a picture of our proposed solution and its system architecture. You'll see the STE and gypsum remain along with the custom I/O boards. However, the STE Computer is now replaced with an NI-PXI chassis using an NI-PXI controller and also 3 Rio 7842R boards, which meet the I/O requirements of the system. For our design, we basically use the real-time aspects of the controller to control processing commands for testing, and then use the FPGA aspect of it in order to relay data back and forth. In order to meet the aggressive schedule for our proof of concept demo, we relied on some support from NI to do that. First and foremost, they were able to provide us with loaner hardware to complete the demo, which not only lowered the cost of our demo, but allowed us to bypass procurement initially and get right into the development and meeting the specifications of the system. Secondly, they were able to provide us with technical support in the form of design reviews, which proved invaluable. They were able to point out certain pitfalls that we would encounter down the road, and therefore we could avoid them as our design went forward. Also, in regards to maintenance, our customer expressed an interest to have a system they could maintain for the next 20 years. And I was able to work with us to combine both their software support plan with their premium system assurance plan to create a bit of a hybrid maintenance plan. The software support plan basically gives you access to their application engineers via telephone and email. However, the premium system assurance provides you with 5 years of warranty service, so they could then evaluate the products in the system after 5 years, and those that are no longer active would be candidates for a technology refresh. In addition, this also includes 5 years of calibrations from NI. In regards to enhancements to the STE, there were several that came from this effort. However, none were more important than the reduced risk to on-orbit assets. Basically, they would no longer have to disable certain elements of the STE in order to test flight software, which leads to faster patch verification and development, and also allows them to fully verify their patches on the ground. In regards to the SVIL benefits, it introduced a new capability to our lab and furthered our simulation domain, while pioneering the use of LabVIEW and NI hardware for our hardware-in-the-loop testing, while also allowing us to enter into a new adjacent market with more possibilities and potential growth and expansion for our simulation capabilities. And with that in mind, I'd like to entertain any questions you may have. Sure. Yes.
For GPS data.
Mm-hmm.
And I was wondering if you could tell me, how do you load in configurations of the ephemeris, where are these satellites, and are you able to like save state and restore, or is this like a model that just tracks where they are currently?
So in regards to gypsum, we actually, for the proof of concept demo and for our final design, we aren't involved with it right now, basically. So we're working through the steps of this. In the next week or two, we'll be beginning basically overhauling gypsum and looking at it. So I don't quite have an answer for that. I would say for uploading ephemeris data, we controlled that through basically the ASCII stimulus files that existed for the current system, and just basically found a way to import those files into our system and load that data to the SPU. So
you essentially, you can go to any state as long as you have the data for it, and that's
yes.
And then is that something that you can do at runtime? Like, could you test what happens if my position jumps 3 meters because, say, I have previous data and all of a sudden the satellites move? This is like what happens if, say, the hardware, there was bus connection or something and data was lost, as an example.
My initial feeling is yes. I'm not entirely positive on it, though. We can talk after if you'd like. Sure.
I have one more question.
Sure.
Is this better than SoftSet?
I'm not. I would say I'm not certain. I don't have a ton of familiarity. Actually, this was kind of my first foray in our lab, so this is my first exposure to it.
I think that goes back a little to maybe first explain a little bit of GPS. So this is simulating an on-orbit GPS satellite. So the simulation is not. So this represents our flying GPS satellites. It's so the GPS sim is actually simulating that vehicle.
I'm sorry, for some reason I was thinking it's
what
applied.
happened is we launched all the vehicles. There's no more left on the ground. So we're really validating flight software in a CNDH unit, for instance. So it's the actual, just like the last previous presentation about how you want to run the real flight software from the real flight unit, and then you need to, have a simulator around that. So that's essentially what they're trying to do, and the preference is to validate patches as the vehicles degrade on orbit and have anomalies. You have to develop patch routines for that, and so you have to have an operational ground test bed, or basically flight hardware that you launch.
So the vehicles that are using this satellite, they're in orbit. Therefore, we've seen this on the NASA project where when you do GPS in orbit, you can't use like a GPS unit you buy at the store because the calibrations are totally different, right? So when you say you deal with the ephemeris data, you have data for that scenario as opposed to where he said ASCII sim. Where'd you get that?
So that's like from the way it was explained to me was basically they were the test scripts for the system to test whatever scenario. So they were pre-programmed by the test engineer.
Okay, so you took stuff for like say a software sim. And you fed it in. Okay, I'll talk to them. I'm sorry.
Yeah, no, that's fine.
Any other questions? No? Very good.
Okay,
Thank you.
Thank you. So,